do hope it won't lag though. So today we're going to cover about sets. And okay, so for most of these, we're just going to cover like the definitions and look back at what is the terms that is usually going to be used in sets and Venn diagrams. So a set is a collection of several like objects or numbers. Like for example, in a set you can technically have anything. You can have a square, a triangle, a circle, or maybe like numbers 1, 2, 3, 4, 5, or maybe you want to have different kinds of clothing, like t-shirts, and then those formal wears or whatever. Like as long as they are grouped together, that's what you usually call a set. But in mathematics, we usually express the set in forms of brackets. And we usually separate the objects by adding a comma. So for example, in this particular set, we can have 1, 2, and that would be one set. And these numbers inside the set, they are called elements. Same with these different sets. So like these different distinct objects in mathematical sense, they're called elements. And then we have several common notations that we use, which is this weird sign. And basically what this means is that in terms of words, it usually means something, something is an element of something. So for example, commonly you can see like X is an element of R. Okay, so there are several definitions of what this means, but since we're following IB standards, let's just assume that R refers to, if I'm not mistaken, R refers to real numbers. So in this case, we can say that this particular element can be any real number. And then if they have, for example, X is crossed, this crossed out
Not
E.
a noun.
Yeah. And then, for example, they say C plus, then it means that X is not an element of C plus. And in this case, C plus means positive integer. So X is not 1, 2, 3. So X can only be 0, -1, -2, -3, and etc. And then there's also the symbol of N of A, or usually like N of something. So usually the one inside this thing, for example, in this case, this is A. This is usually the name of the set. So for sets, usually they have like a symbol that represents a set, and most of the time the symbol is a capital letter. It can be in the form of U, it can be in the form of E, or it can be in the form of X, but X is usually overused, so they usually use like A or B. So in the set, usually there's some elements, and when you have this particular symbol, they're trying to ask how many elements is there in the set. In this example's case, you have 1, 2 elements. So you can write that NA equals to 2, assuming that this is this particular set is A. Okay, so since I've covered this one, I'm gonna now go into this one and clear up the screen. Okay, so next. So in sets, since there are many kinds of sets, there's also many ways to express sets. For example, if you have set A and then you also have set B, and if, for example, they contain the same element, like in this case 1, 3, 5, and this one also has this exact same set, then we can say that A is equal to B.
Can you minus sets from each other? Can you subtract sets?
You can't subtract sets.
Okay.
I mean, not you. Like mathematically speaking, you cannot subtract sets. But for example, if you have, let's just say if you have P and Q, and then assuming Q is 2, 4, 5, they have 2, 4, and 5 as their elements, and Q has 2 and 4 as their elements. Then if you want to say like P, you can't really say P minus Q because that's not really valid, because something like this assumes that P, Q, 2, 4, 5. So it's just kind of like a form of grouping elements. It's not addition, subtraction kind of thing. But if you want to like look for the set that's outside of it, there are other notations that you can use to express that. And I think we're gonna like pretty much cover that up later.
All right.
Okay, and then there's also subset. So subset is denoted by this symbol, and if you have this kind of thing, it's usually kind of like saying that
It's inside.
yeah, it is kind of like saying that, for example, if this is B and this is A, the elements in A exist in B in some way, like they have the same set or less.
Like, for example, natural numbers is a subset of real numbers.
That's correct. So natural numbers, and then this is real numbers. It's also the same with proper subset, but the difference between the two is that I think a subset can be equal to the elements in like subset can be equal. Well, in proper subset, it can't be equal. It's like one inside the other, like this particular example.
So in subset, they can just be the same.
Yeah. And then there's also empty set. Empty set basically means that there's nothing in the set. So empty set. Usually if you want to draw, if you want to draw the set, it's just like empty. But then, so you put on an X sign in it. Or if you want to express it in mathematical symbols or notations, you just add the brackets and with nothing inside. We also sometimes call this null. I think in IB they only accept this or this because I didn't see this in the textbook, but in my experience in IGCSE, you can use the word null, and that would express an empty set.
Mm.
And then there's also finite and infinite set. Finite set. This is pretty self-explanatory. I've at least in like high school level, I've never seen encounters with infinite set, but we always encounter a finite set.
Alright.
Okay, so we're going into intersection and union. Finally, Venn diagrams. Okay, so this is a Venn diagram. You should know about this, or else I am concerned about your mathematical knowledge. Because you're expected to know this before you go into IB, but okay, so an intersection and union. So this is intersection and this is union. I don't know how people usually do it. Like, I think there are times when people confuses the sign U and N, but like how I usually try to remember is union is in the form of U, and like the shape kind of like in my like in how I express it, the shape is kind of like taking account into everything. Like U, it I usually imagine it as if like the U involves everything, while the N is restrictive, so it only takes certain areas, which is why the intersection usually only takes the elements that are involving both sets. Well, for union, because it includes all, it covers all, it's usually like this.
Mm-hmm.
There are times when the intersection doesn't exist. Wait, sorry, not doesn't exist, more like they have an empty set. So they don't have intersection. This is usually seen in the case when two sets are mutually exclusive, like this. So what they mean by mutually exclusive is that the two sets doesn't meet, or they don't their values don't overlap. So they're like exclusive or separate on their own.
Yeah.
And hence you cannot shade you cannot shade an intersection of this. I apologize. This is supposed to be N, A, and B, not union.
Okay. Can you string intersecting unions together, like in a triple Venn diagram, for example?
Oh, like this?
Yeah, and let's say ABC.
Okay.
Then what would be? Could you write A union intersect C?
Unit
A union B intersect C.
intersect C. Is this the are you supposed to bracket it up this way?
I am Not sure. It's been a while since I've done
Oh,
this. Because we
okay,
don't do it in the
so
linear system.
if there's this kind of thing, they usually always put in brackets either here or here. There's always brackets. There's no such thing as like this.
Yeah.
So let's just assume that it's A union B, like this, with this bracket. So you start working on this part first. So A union B is here. Okay, I'm just gonna draw a tiny one here. A, B, C. A union B would be this. And then it's gonna have to intersect C. So C is this part. And the ones that overlaps twice with A
Yeah.
union B would be this part.
Right.
Mm-hmm.
It's not that hard.
So, sorry, what was your question again?
No, it's just I wanted to see an example.
Okay. Okay, so this in Venn diagrams, this rectangle in IB is usually called U. I don't know why. Probably because it's universal set. Usually, it means like
Everything,
the
right?
yeah. It's kind of like the world of the set. The I usually think of it as like the world of the sets. So in this world, we have, for example, in this world, we can have a set A and B, or maybe in the other worlds, we can have A, B, C, and then in other worlds, like aka in other examples, we can also have weirder examples like A, B, C. And this all varies in different questions. It just depends on how the question is designed. But the more common ones would be this and this.
Yeah.
And then complement. So when there's a set and then there's this accent, there's whatever this thing, I don't know how you call it. I just usually call it an accent. It means the complement of it, which is complement. Um, so for example, if you have A, set A, then the complement of A or A accent would be this part of it.
Mm-hmm.
It's kind of like the opposite of it.
Yeah.
It is pretty much the opposite of it, technically. In there are some of these rules about complements of a set, which is basically pretty much derived on how they are in nature. Like they say that A intersection of A accent is an empty set. And we can see that because they're literally the opposites of each other. They don't overlap. So
Mm-hmm.
technically it makes sense. And then there's also A union A complement, which equals to U. And this also makes sense because it's like um it's like one part of the universe plus the other
Yeah.
combined all together. So it becomes the entire this entire universe. And then they also have the number of A plus the number of set the number of elements in the set A and the number of elements in the complementary is equal to the number of elements in union. And again, this is also pretty much derived on how the nature of the Venn diagram works.
Alright.
Hmm. Okay, so I'm gonna reset the annotation and scroll down. Okay. So I think in like every course they have their own special number sets, but this one is the IB version of the number sets, and this is pretty much like this is like the same as the general.
Wait, is the complex plane covered?
Hmm?
Is imaginary and complex numbers covered?
Imaginary numbers are no, we only have these.
Alright.
I don't think we have. I mean, if we have imaginary numbers, they probably use the general notations for them. Like imaginary is just I, the usual.
Mm-hmm.
But specifically for these, sometimes there are variations to it. Like in I forgot. I think in IGCSE, the one I learned is that R is equal to rational numbers. But again, this is IGCSE.
Mm-hmm.
But now since we're in IB, R now becomes real number. So it really depends on the syllabus. This is like um, C plus and then N C. This is rational.
Irrational
Yeah,
is like a
this
separate
is
one.
uh-huh. Here's the real numbers, and then here's a tiny irrational.
Yeah.
Wait, oh no. Oh wait, this is irrational, and then this other part is pretty much the irrational part. This is
Yeah.
real, and then this is the entire number world. This, this is pretty much how the IB version works. Okay, so now we're going into intervals. There are there mathematically in IB, there's two ways to write intervals. The first is this kind. It's called interval notation, and then this, oops, and then the second is this. So um, this usually is the part where they show the range of the numbers that's applicable. Well, this one shows the set of numbers. And for this part, sometimes they would express it in a way that it's like XER to kind of like establish it's kind of like to establish the universal set of what is generally applicable in the intervals. I don't know why they do this, but Yes, they do it that way. Okay, so other than the mathematical way to express notations, there's also the graph way, the more visual way to express it, which is called number line. Basically, how you do it is you just make a line, you draw the values, and then if it's, for example, if it's this value, then you make a line from the values that are supposed to be covered, and then you draw a circle. So if the value doesn't include the number, like in this case, because you don't have the sign with the sign underneath, yeah, the equal sign, then usually you don't fill it in. But if you have something like, for example, 2x 3, I don't know how to mathematically describe that. I'm so sorry. I can just write it down. This is 2 over 3. You draw a line, you make a circle, and then since you have the equal sign, you have to fill the circles in to show that the values are included.
Mm-hmm.
Hold up. Something just popped in. Okay, so there are also cases where, for example, your value is just like x smaller than 3. So you just pull a line, and then you just draw this, and then you just put an arrow to express that it goes to
Continuous.
infinity. Yeah, it continues all the way. Okay, so in this intervals notations case, if there's this kind of form, you can just say x is less than 3. But in the bracket notations case, you need to draw, um, you need to express it infinity and 3. I'm not sure if you're supposed to express it this way or you're supposed to express it the other way. But I'm assuming that you have to express it in this way since it includes infinity. Logically.
Mm-hmm.
And and this is like pretty much it for the theory for Venn diagram regions and problem solvings. Oh, so it's supposed to be. So is it supposed to be like if it's exploded? Is it supposed to be like this? Ah, okay. Interesting. Okay, so for these two, you're supposed. I kind of already like drew all the stuff before, so we can just jump right into the questions if you want.
Sure.
Okay, so I can just stop screen sharing this and move it to the the high say textbook because I took questions from there. I'm stealing it. I mean, you can just pretty much go right into some of these questions. Okay, let's just start easy and do number one.
Mhm.
Mm. Okay. Should I give time for you guys to try it out, or should I just go right into it anyway?
Just up to you. Usually,
Yes. Okay, I'm gonna give like 1 minute.
yeah.
I don't know if that's enough time, but yes.
Can the same element occur twice in a set?
Technically, yeah. Oh, but okay, I think it depends on the context, because for oh, that's 1 minute. Okay, so the thing here is that this is a set of letters, so I'm assuming that one letter counts as, if there's two letters, you just count it as one in the set. So kind of like V and so A would be VN, but then B would be DIAGRM. I'm just gonna give more time to work on the rest. Oh, sorry. Okay, so I guess I'm gonna start explaining them.
Yep.
Okay, so since I've covered, oops, I forgot to annotate it once again. There. Okay, so since I've covered part A, I'm just gonna skip that. Okay, for part B, you're supposed to find the element of A and B. This is, I mean, if you see this and this, it's pretty much just 3 and 1, 2, 3, 4, 5, 6.
Yep.
And then for C, you're supposed to find A intersection of B.
That's
And
no or
from these sets, you can see that they don't have any same elements, so it's just mutually exclusive. It's empty, so the comment would be mutually exclusive. That's it. That's the keyword that you have to hit. You can explain any use any kind of big words, but if you don't say mutually exclusive or it's an empty set, I think you don't have to say the empty set, you just need to say the mutually exclusive part to get points. And then for part D, A, decide whether the statement is true or false. So they say that phi is not an element of A, and that is wrong because you can see the phi here. For the second, so this is false. G is an element of B, which is true. It's right here. Then for the third one, is the number of element in A and number of element in B is the number of element in A union B, which is true. Since they are mutually exclusive, that means that if you add, if you unite them together, their elements is going to stay the same since you're just adding 3 and 5 together separately. It's not like they overlap or anything. So some of they're not going to like because the thing with uniting elements, if they're like not, if they're together, if they have some sort of intersection, is that you some of when you're adding the elements like na plus nb, some of the elements you can see is gonna kind of like double.
yeah.
So you're going to so you're not going to have the same amount as um, number of number of A union B, because A union B kind of like unites everything, but also try to make sure that the middle part doesn't double.
Mm-hmm.
So yeah. Okay, so we should probably cover more questions. Oh, this is okay. Maybe we can cover a hard question. We can try question 10. Here. Oops. I'm gonna give time to work on it. I'm gonna give 3 minutes to work on it. Hopefully that's enough. Okay, it's been 3 minutes.
Mm-hmm.
Did you get the answers? Or did you not do
Yeah,
anything? Oh, nice.
I got the answer. I mean, I think I got the answer.
That's nice. Okay, so in this, the union has 564 students. And then during term 1, during term 1, 299 of them is absent for at least 1 day. And then 111 missed some school because of family holidays. Let's just say this call this as sick. And then this is family matters. But then there's also 296 students that attend school every day. Let's call this Oh, let's just have says every. So showing that one person is sick and another has some holidays. Then I presume that the Venn diagram would look like something like this. This is sick, this is family, and then the rest of it tends to every day.
Mm-hmm.
So if you want to look for, since we know that there are students that comes every day, that means that we can look for the students that doesn't come every day. And you do that by doing 564 minus 296. And that results in 268. So you can kind of say that the complement of 296 is 268, or S union F, the opposite of this part right here. Okay, so with this number and some of these numbers, you can finally find each section of these. So we can find the people who only miss school because of sickness, and we can also find the people who only miss school because of family business. Because obviously, and if in these different circumstances, there are also people. We can also assume that there are people who are both sick, who has ever been sick and who has ever had family businesses. And if you're not sure if they do have it or not, an easy way to determine that is to add these two values and compare and see if the two values they have is bigger than the number of students. Because you can't have more,
Number
more
six.
students or numbers that are bigger than 564. That's impossible.
Yeah.
Okay, so since we have to display this information in the Venn diagram, that means that we have to look for every part of the Venn diagram. And you have to use this number. And for example, if you have this number and you have this number, you can do 268 minus 229, and that will find you the people who only has only skip school because of family businesses. And that would result in 39. So you found that this is 39. And then to find the middle part of it, the people who skip school because of sickness and family issues, we can just minus 111 with 39, and that will give you the rest of the people in this circle. And then to get this, you can either do 229 minus 72, or you can also do 268 minus 111, and it will result in the same answer, 157. And after you get all the values in every part, that's when you finish number one. And for the second one, find how many students who missed illness and holidays. Oh, we missed school for both illness and holidays. You've pretty much found this one. It's right here.
Mm-hmm.
It's 72. We're away for holidays, but not sickness. That would be 32. We're absent during term 1 for any reason. That would be
Total.
the opposite of the non-absent people, so that's 268. Okay, that's it.
Yep.
Okay, time to do the harder questions. I mean, maybe we can do something like, okay, we can do something like number 5 first before jumping into some other questions down there.
I think I'm done.
Hmm?
Yep.
Is that it?
It wasn't that hard.
Yeah, it's pretty easy. So list the elements of S. 2, wait, not 2, sorry. 3, 4, 5, 6, 7. Very easy.
Yep.
And then display S on a number line. So like before, you draw the number line first. You put in the values that is supposed to be the part of the elements, which is 2, 3, 4, 5, 6, 7. And then don't forget to add the arrows to show that it's a number line. And then you forgot to pause. And you just pull it from 2 to 7 and
Yep.
make a circle and shade the ones that are included. That's it.
Yep.
Find n, the number of element of S. That's 1, 2, 3, 4, 5. So that's S5. Done.
Mm-hmm.
Okay. So now we can. I'm interested in doing number 12. We should do that one.
Pardon?
Doesn't number 12
Uh,
doesn't seem that hard though. I've seen harder ones. Let's do it anyway. Oh, my timer's over. So
Yep.
I guess we can start discussing about this. Okay, so at a conference, 58 delegates speak many different languages. So in this conference, we have a total of 58 people. There's Arabic, Chinese, and English. You can assume that there's going to be 3 sets: Arabic, Chinese, and English. So there's 28 people who speak Arabic, 27 who speak Chinese, and 39 who speak English. Oops. Got it upside down. Arabic. Okay. There's 12 people who speak Arabic and Chinese. Chinese and English would be 16, and then Arabic and English is 17. And then Q. Oh, hold up. Oh, oops. It is both of them only. So, when they mean both of them only, it's not a union, it's an intersection, because it's not either. It doesn't include the people who only speak Arabic and then the people who only speak English and the people who speak both Arabic and English. They only ask for the people who speak Arabic and English at the same time. So my bad on that part. So it's supposed to be a union, and then so if they speak all of them, then that would be 2. So in this tiny spot, you can write a 2.
Then you just minus 2 from the intersections.
And to find the rest of these, since you already have 2 right here, you can just minus 2 to all these numbers to find this like petally like shape. So if this is a union E 17 minus 2, that would be 15. Okay, so you see the answer is asking for you to answer some of these, but I usually have a habit of drawing the Venn diagram and filling in all the spots first before answering it, so we should do that first. It C intersection of E would be this: 16 minus 2 is 14, and then 12 minus 2 is 10. And then now with this, you can easily find this part by doing 28 minus 15 minus 2 minus 10. And that gives you
1.
Yeah, that gives you 1. And then you can do 27 minus 2 minus 14 minus 10. That gives you another 1. 29 minus 15 minus 14 minus 2. And that gives you
8.
That gives you 8, yeah. So this is 8. And then to find, you also need to find the ones outside of this. And that would be 58 minus all these numbers. Or you can also just do like minus 39 minus 10 minus 2. minus 2. And that equates into 58 minus 49 minus 2, 56 minus 49. That's
17.
that's 7.
17.
Yeah.
Wait. I might have gotten it wrong. Yeah.
Yeah, that's 7. So now you can finally answer all these questions smoothly without getting confused of what you should do. Because you already got all the answers.
Yep.
Okay, so how many delegates speak Chinese only? 1. How many delegates speak none of these languages? 7. How many delegates speak neither Arabic or Chinese? So if they don't speak Arabic or Chinese, it's the, wait, let me just, okay. Basically, it's the opposite of this, anything that's outside this. So that
Yep.
includes this part and also this part. So that means that's 8 plus 7, which equals to 15. Okay, that's it. Pretty easy.
Mm-hmm.
And I think, well, that's pretty much it for today. Thank you for coming for this session.